We all think we have a pretty good handle on probability, right? Flipping coins, rolling dice, easy stuff. But what happens when the possibilities are infinite? When you try to pick one exact point out of a billion, or an infinite number of points? Suddenly, our intuition just breaks. It turns out modern probability is built on a secret foundation, a really rigorous rulebook for dealing with infinity. And that rulebook is called measure theory. Okay, let's just dive right into the weirdness. Imagine you've got a number line from 0 to 1. If you could throw a dart and hit it, what's the probability you'd hit the exact point 1/2? I mean, not 0.50001, but the infinitely precise number itself. The mathematical answer? It's 0. But wait a second. The probability of hitting somewhere on the line is 100%, right? So how can a bunch of 0 probability points, an infinite number of them, add up to a sure thing? This is exactly where our everyday logic just completely falls apart. The whole problem really comes down to the switch from finite to infinite. With a 6-sided die, it's a piece of cake. You've got 6 outcomes. What's the chance of rolling an even number? You just add up the probabilities, 1/6 for a 2, plus 1/6 for a 4, plus 1/6 for a 6. Simple. But with a point on a line, we've got infinite outcomes. And we already said the probability of any single one is 0. If you try adding up zeros even an infinite number of times, you still get 0. Our simple addition tool is completely broken here. We need something else entirely. And this is exactly where measure theory steps in. It is the formal, super rigorous rulebook that was designed specifically to handle these kinds of tricky situations with infinite outcomes. It gives us a consistent way to measure the probability of sets of numbers, even when just adding up the individual points gets us nowhere. So, if we're going to build this rulebook, we have to start with the absolute basics. The very first step is to clearly define the playing field for any probability problem. We've got to know what all the possible outcomes are, and maybe more importantly, what kinds of questions we're even allowed to ask. The whole structure that mathematicians use is called a probability space. You'll see it written as this little trio of symbols: omega, F, and P. Now, it looks pretty abstract, I know, but it's really just 3 core components. Omega is just all the possible outcomes. F is the collection of things we can ask about, or events. And P is the function that actually gives us the probability for each of those events. Let's break each one of those down. First up, we've got omega. This is the simplest piece of the puzzle. It's nothing more than the set of every single possible thing that could happen. For a coin flip, omega is just a simple set containing 2 things, heads and tails. For our dart throwing problem, omega is the set of all the real numbers between 0 and 1. It's basically the universe of all our possibilities. Next is F. Now, this one's a little more subtle, but it's incredibly important. F is often called the set of events, but I think it's way more helpful to think of it as the collection of all allowable questions. For a dice roll, an allowable question could be, was the roll an even number? The event is then the set of outcomes that makes that question true, the numbers 2, 4, and 6. So F is kind of like the master list of all the questions that we can meaningfully assign a probability to. So what makes a question allowable? Well, this collection of questions has to follow 2 key rules. It has to form what's called a sigma field. First rule, if you can ask about an event, you have to be able to ask about its opposite. So if we can measure the probability of rolling an even number, we also have to be able to measure the probability of rolling an odd number. Makes sense, right? Second rule, if you can ask about a bunch of separate events, you also have to be able to ask about their combination. So if we can measure rolling a 1 and also rolling a 2, we must be able to measure rolling a 1 or a 2. These rules just make sure our system is logically sound and doesn't have any weird gaps. Okay, we've defined our playing field with omega, and we've set up the rules for asking questions with F. Now, we need the actual tool that does the measuring. This is the third and final piece of our whole probability space. And that tool is P, the probability measure. It's basically a function. You hand it one of those allowable questions, an event from our collection F, and it spits back a number between 0 and 1. And that number, that's the probability of that event happening. This is the piece that connects our whole abstract setup to the actual numbers we all think of as probability. And for P to be a fair measuring tool, it also has to follow some common sense rules. First, probabilities can't never be negative. Obvious, right? Second, if one event is totally contained within another, its probability can't be bigger. This is called monotonicity. Think about it. The probability of rolling exactly a 2 can't be greater than the probability of rolling an even number. And third, for any group of non-overlapping events, the probability that any one of them happens is just the sum of their individual probabilities. This is called countable additivity, and it's the superpowered version of the rule we used for the dice. It guarantees our math works. All right, so now we have the complete blueprint for a probability space. We've got outcomes, we've got allowable events, and we've got a measuring tool that follows fair rules. But this brings us to the real core challenge. For a really complicated space, like all the numbers on a line, how in the world do you actually build a measure P that satisfies all of these rules for all the possible things we might want to ask about? The strategy of measure theory is actually brilliantly practical. It says, hey, don't try to measure every complicated, crazy set all at once. That's too hard. Instead, let's start with some really simple, basic building blocks that we definitely know how to measure. And once we've nailed that, we can figure out a system to extend that measuring ability to more and more complex shapes that we build from those simple blocks. So these basic building blocks have a fancy name, a semi-algebra. But honestly, just think of them as Lego bricks. For our number line example, our Lego bricks are just simple intervals. For instance, all the numbers that are bigger than A but less than or equal to B. We can easily define the measure or the length of a block like that as just B minus A. These are the simple, easy pieces we're going to use to build everything else. And this brings us to the single most powerful idea in this whole thing. It's called the extension theorem, and it's basically a profound guarantee. It says that if you can define a consistent way to measure your basic Lego bricks, like we just did, then there exists one and only one way to extend that measurement to every complex shape you could ever possibly build from them. It's like mathematical magic. It lets us go from measuring simple lines to calculating the probability of really complex abstract events. This theorem is the engine that does all the heavy lifting for us. Okay, I know, that was a lot of abstract machinery. Omega, sigma fields, measures, all that. But what's the payoff? Why does building this whole formal structure actually matter in the real world? Well, it turns out this is the hidden foundation for some of the most important fields in modern science and technology. This framework is so much more than a mathematical curiosity, it's absolutely essential. It provides the rock-solid foundation for any probability problem that deals with continuous spaces, which are everywhere. It's what resolves all those paradoxes where our intuition just gets it wrong. This is the language of modern probability, and it's the engine running under the hood of everything from financial modeling and data science to even quantum physics. When it comes right down to it, measure theory is what gives us the power and, more importantly, the confidence to assign precise probabilities to unbelievably complex events. Whether we're trying to model the random wobbles of the stock market, analyze gigantic data sets, or describe the probabilistic location of a subatomic particle, it all rests on this incredibly rigorous foundation. So let's end right where we began, with that initial mind-bending paradox. If every single individual point has a probability of 0, how can an interval, which is just a collection of those points, suddenly have a positive probability? The answer, it turns out, is that measure theory forces us to shift our thinking in a really fundamental way. It shows us that for infinite sets, probability isn't about adding up impossible things, it's about measuring possible things. And that simple-sounding change in perspective, well, that makes all the difference.